Oh, hi there. Thanks so much for showing up for the second half of this lesson. We're going to go over some more of the challenging examples. We only got a couple left, but again, we're reviewing our skills about factoring polynomials. So we're going to give this one our best go and see how we do. One thing I notice is, what do you notice about this function here? 2x to the 4 plus 5x cubed.
It's already to 0.
Yeah, it's already set to 0, so that's convenient. That's a great observation. What else do you notice?
There's a quadratic formula on the top right.
Yeah, I have a feeling we might need that. But probably, there's certainly going to be some rational roots that we can find with our skills. So what are some of the candidates for numbers, some of the potential factors that might be working here? X might equal
1, 2, 4, 8.
and plus or minus any of those, right? Yeah. 1, 2, 4, or 8 are the factors of 8, so that's very good. And then we should also consider 1/2. 1/2 is in play because we could be taking 1 and dividing it by that. That's the only one that might be an issue. That might be like a little trickier. So which one you want to test first? 1. Does it work? Yeah. You just add the coefficients together, because if x equals 1, then that thing's a factor. So when x equals 1, you're just ending up adding the coefficients. These ones balance, like they're 0. And then minus 10 plus 8 plus 2 is another 0. So it's actually pretty nice to see it that way. So we know this one is x equals positive 1 is for sure a factor. So let's divide that out. X minus 1, remember to sign flip. We're going to divide that into 2x to the 4 plus 5x cubed minus 5x squared minus 10x plus 8. We multiply by 2x cubed. That's going to give us 7x cubed here because we subtract that thing. So 2x cubed times x minus 1 is, these cancel. So we're on the right track. We drop down that minus 5x squared. We're going to multiply by plus 7. So plus 7 here. Move my useless face. 7x cubed minus 7x squared. When you put this in brackets and subtract it, I think it's easier to see that we end up with 2x squared. So that's why I do it that way. And then we drop down that minus 10x. Multiply by, I dropped my x squared there. No problem. We had it in our brains as we did this. Okay, so I want to create a 2x squared, so I need to multiply by plus 2x. And when I do that, I get 2x squared minus 2x. And then I do the whole subtract those things, and that gives me minus 8x, which is great, because then when I drop down this plus 8, I can see that when I multiply by minus 8, I get 0 remainder there. So I put in my happy 0 remainder, happy face. Okay. So we could rewrite this right away as x minus 1 multiplied by 2x cubed plus 7x squared plus 2x minus 8. And we know that all of that is less than 0. But we're not done because we still have a cubic in there, and we want to know the cubic zeros. So we only know one of the zeros so far is at 1. So let's try our tricks again. We still have the same potential factors, and I'd encourage you to test 1 again. Even though we can look at it and see it doesn't work here, we tested it. 2 plus 7 plus 2 minus 8 gives us 3, and 3 is not 0. So 1 is not a factor anymore. Let's try minus 2, and minus 2 doesn't work either. Sorry, minus 1 doesn't work either, because then you would have minus 2 plus 7 minus 2, minus 8. When you're testing minus 1, just all of your odd degree x's flip their signs. So that's not 0 either. So we've got to test 2 or 4 or something like that. Let's try positive 2. Positive 2 clearly won't work because 1 was already too big, so 2 would be well too big. So let's test minus 2. Anyone else see it? See the one that we're missing? Should we test minus 2? Minus 2 here gives us minus 16 plus 28 minus 4 minus 8. Doesn't that look good? Yeah, so minus 2 is another factor. Okay, so now I'm just going to switch into another color, really zoom in so I have space to do my division, and I'm going to rub out our rough work. We found that x is minus 2 is one of our factors. And we're keeping a list here because, you know, we're going to have them in the factorization, but those are our zeros, and that's really what we're hunting for. So let's go. When I divide x plus 2, because don't forget to flip the sign, into 2x cubed plus 7x squared plus 2x minus 8, we get 2x squared, multiply there, 2x cubed, plus 4x squared, put that in brackets and subtract it, gives us 3x squared. These, of course, cancel perfectly, plus 2x. And we're going to multiply here by plus 3x, multiply through 3x squared plus 6x, put that in brackets and subtract. Good thing we do because we get minus 4x, and isn't that nice because this minus 8 drops down, and we see we have the same ratio here as we do there. When we multiply by minus 4, we get our 0 remainder. There's my 0 with the happy face. So, rewriting this whole expression again. You can do this in one line or 2 lines. This part is like keeping the main flow of my solution together. Two x squared plus 3x minus 4 is less than 0. Okay, so now I'm looking at this, and now I wonder, hey, is there a way to multiply to negative 8 and add to positive 3 across the integers? Does this factor by grouping or something like that, by trinomial factoring? Nuh-uh. But does this thing have zeros? 2x squared plus 3x minus 4? Will we find roots? Is it worth using the quadratic formula here? Yeah, how do you know?
Because we can't factor it the other way, so to find the factors, if it gives 2 answers.
Yeah, it will give 2 answers if we use a quadratic formula, and it's quadratic, so we're expecting 2 answers. But sometimes these things don't have roots, like they turn around above the x-axis. But this one here has a y-intercept of minus 4, and it's opening upwards. So it definitely hits at 2 points. Because it has this end behavior, 2x squared plus 3x minus 4. So, and it has a y-intercept that's minus 4. So I visualize and know that it has 2 roots. Another way to check is just to check the discriminant. If you prefer to work algebraically, right, Gavin? You would probably work algebraically.
Yeah.
Oh, yeah. Okay. All right. I thought you were like really right with me. So there, like b squared minus 4ac, because c is negative, that's going to end up being plus. So we are positive. We have a positive discriminant. So yes, it's definitely worth checking with the quadratic formula. So when we're doing the quadratic formula here, let's flip colors again to show this different type of work. We have a is equal to 2, b is equal to 3, and c is equal to minus 4. Just grab out your coefficients, and I encourage you to make a little cheat sheet for yourself, because when you go ahead and substitute into the quadratic formula, opportunities for errors abound. So you have x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. And then we sub in. X is equal to, yeah, this is as small as my pen gets. Okay, so negative b is negative 3, plus or minus the square root of 3 squared is 9, minus 4 times 2 is minus 8, minus 8 times minus 4 is plus 32. Ew, gross. Okay, and then we have all of that over 4. 2a is 4. Okay, so I can check here visually and just like go back and check this line to that line and make sure everything is correct. 4 times a times c is indeed 32, and it's positive because it's negative, negative. And then b squared. Yeah, so I'm good. So I carry on one more line, and we have x is equal to negative 3 plus or minus root 41 over 4. Anyone know anything about root 41? Oh, hi, Hayden. You were here at the beginning? Okay, I'll change the attendance in a moment. Okay. Yeah, it's in between 6 and 7. Yeah, good. Yeah. So, but it is 41 is prime, so this is certainly can't be like simplified at all. That's why I said ew, because we got a big prime in there. So it's kind of gross. Okay. So anyway, this is roughly equal to, if you have negative 3 plus 6 and a bit, then you're 3/4 and a bit. So just to put it roughly on the number line, or negative 3 minus 6, then we're like minus 9 on 4-ish. These are not accurate. They're just to get us in between our other roots or properly space them out on our number line. Okay, so now we can build our number line. So let's go ahead and do just that. So we know that we have a root back there at minus 2. But we have one that's even further back at minus 3 minus root 41 on 4. Okay, that's one of our roots. Minus 2. See, minus 9/4. I did that little check to know that that one would be less than minus 2. So just ordering them correctly on the number line. Yeah. You feel me. Okay. And now 1 is one of our roots. But so is 3/4. So we have 3/4 comes first. No, it's not 3/4. It's minus 3 on 4. Minus 3 plus root 41. Let's be accurate, on 4. And then we have here 1. Okay, cool. Now, let's choose some values in between all these things that we can use to test our function. Okay, so if we call this f of x, that's just like just a little thing that I'll do here to make this easier to notate. So when I'm going to test this, I could test f is negative 10. That's for sure way to that side, much closer to negative infinity than this. Based on the visualization here, we've got no bounce roots and stuff. We have this end behavior, so I'm expecting this to be positive. So we're going to test that out. And would you look at that? This one here overwhelms all the other terms. That's 20,000, but positive. When I put in f is negative 10. This is negative 5,000, but 20,000 minus 5,000, like there's nothing that those can do to get close to bringing that below negative. So this one is positive in this interval. Okay, so I can test it in this one if that's easier for me, or I can test it here this way. If f is negative 10, then this is negative. Okay, this is negative 11. This is negative 8. And this one is positive 200 minus 30 minus 4. So that one is positive 164. And negative times a negative times a positive is a positive. So we are positive in this bit here, and that matches our end behavior, what we already knew from visualizing, because we're smart folks who do the problem 2 different ways to check our answers. Good. So now let's test something in between here, and gosh golly, it's really hard to find something that's just quite in between there, isn't it? Let's do negative 2.1, because that is going to for sure be inside this funky root and negative 2. So let's test f at negative 2.1. And yeah, Yeah, because that's a little bit more negative than minus 9 on 4, so for sure that's going to work. Okay, so just going to note that we will be negative here. Okay, so negative 2 minus 1 is negative 3. Negative 2.1 plus 2 is negative 0.1, so we're still negative. And then in this one here, I suspect that we're negative now. That I'm going to have to do on a calculator, so sometimes you just got to turn on your calculator and do that. So here we go. There it is. Where's that calculator? Oh, Mr. Jennings, he uses the calculator so infrequently. So 2 times 2.1, but it's negative, and I square it, plus 3 times 2.1, but it's negative, minus 4 equals a negative number. So we have negative times a negative times a negative in this interval, so this interval here is negative. Okay, let's test something in between here. We know that 0 lies in between there, so that's real easy. Let's test 0. And if you said, well, let's test 0 in this one, I would say, haha, I can test 0 in that one a lot easier. Watch this. Ignore all of those and just see that 8 is positive. So it's very easy to test 0 there, because all of those are just multiplied through linearly. You would find the same result if you did it in the interval table. You'd have negative times a positive times a negative, and that would give you a positive. So we're positive in this interval, unsurprisingly. Each one of these is a cut root. So we are expecting it to change signs each time. It's bounce roots where they're going to be the same on either side of a root. Okay, and so in here we're expecting this to be positive. And we want to be bigger than 3/4 but less than 1. So let's test f at 0.9. F at 0.9 is going to give us 0.9 minus 1 is negative. 0.9 plus 2 is positive. And over here, 2 times 0.9 plus 3 squared times 3 times 0.9 minus 4 is positive. I can do that in my head, not actually figuring out the value, but just know that it's positive. But we'll calculate it anyway, supposing that you can't. 2 times 0.9, and I square it, is equal to 1.62 plus 2.7. 3 times 0.9 is 2.7 plus 4.32 minus 4 is we are positive in here. Why are we positive in there? What? We're positive here. Oh yeah, we're positive in here. Yeah, so we know this is positive, so we have negative times a negative times a positive. So we are in fact negative in this interval. And then let's test something like f at 10. F at 10 up here. Really easy to test there. We have like a bajillion million. It's not a bajillion million, but it's so big that it overwhelms all the other terms. That would be 20,000 plus 5,000 minus 500 is almost nothing. Yeah?
For the 0.9, you said it was negative times positive, but you have one negative and two positives.
No, did I say negative times negative? Oh, it's negative times positive times positive. I misspoke. So that time the thing I was writing down was right, but the thing I said was wrong. That's interesting because usually it's the opposite way around. Yeah. So I appreciate the participation and pointing that out to me because I would have missed that. Yes, for this interval here, this quadratic is positive at 0.9. This one is positive and that one's negative, ever so slightly negative. So yes, you have negative times positive, so that results in negative. This one over here is positive, so no surprises there. So now we have these intervals. We have negative infinity to, oh wait, when is this less than 0? Okay, so when is it negative? All right, so not in this interval, it's positive there, so we don't have the negative infinity one. But we do have this interval here and this interval here where it's negative. All right, so the way we would write that for exact values is minus 3 minus root 41 all over 4 all the way to minus 2, not inclusive, because we are not including these things, it is less than 0. And in this interval as well, between this root and that root, it also works. So we also have minus 3 plus root 41 all on 4, all the way to 1. This function is
Do we do u in the
negative
middle?
as well. Sorry?
Do we do u in the middle? Or
Yes, it's the union of those two things. Those are the two places where this thing is negative. And you might also be saying, Mr. Jennings, I defy you to check that in Desmos to prove it to our satisfaction, and I'm glad that you doubt me to that degree. It's good. It's good to doubt. So we have 2, 5, 5, 10, 8. Let's copy it in. 2x to the 4 plus 5x to the 3 minus 5x to the 2 minus 8x, yes, plus, no, minus 10x.
10x and plus 8.
10x, yeah, plus 8. I was remembering that, and so there. Here is the one interval that we talked about, and here is the other interval that we talked about. Let's, for argument's sake, put in minus 3 minus SQRT as your shortcut there, 41. Put it all in brackets and put it over 4. Okay, put a comma and then 0 for y and make that a point. And look at that, bink. Okay, and then just copy this one and swap the sign there. And you see bink. Okay, so we binked it. And it's highly satisfying to see how close we binked it. Okay, so so our algebra is correct. Our intervals are correct. There's those two little bits where this function peaks underneath the x-axis, and it's negative for those little bits. It's less than 0 for those little bits only. Cool. All right, so that's that one. Any questions about this example? Oh my gosh. It's a long example, and I wish I had more space. That's what I wish, because my work is very all over the place. This one is a nice one. I want to talk about this one today. So, yeah, so let's see if I can organize my work a little bit better here. We are told that the stock price is given by this cubic equation, and we want to know at what times is the stock over $24. Maybe we feel it's favorable to be selling the stock when it's over 24 or something like that. We just really need to know this interval. So, how would you get started on something like that? Like, how do we even use this 24 here?
You plug it into t.
Is that a value of time?
You plug it into p.
It's P of t. So we know that the price of this stock at some time is equal to $24. Okay? So this is our starting equation. We also know that the price of the stock is equal to this. So what we want to know actually is not when is it equal to 24, but when is the price greater than 24. Okay, so we have this inequality. So now let's move that over here onto the left where I've been organizing the flows of my solutions. We would have 24 is less than the price of the stock, written as a cubic. Okay, my next step. Yeah, 0 has got to be less than the price of the stock, oops, cubed, plus 7t squared. That sounds like 70 squared, which would be 4,090. So 4,900. Minus 10t minus 24. We subtract 24 from both sides. Do my alligators need to change direction? No, I was just subtracting from both sides. That's totally cool. It's only when I divide or multiply by a negative that I need to flip my alligators. All right. So now, what are my potential factors here?
12, 2, 1, 24, 8,
Yeah.
3.
1, 2, 3, 4. Oh, there's so many. 6. 24 is such a factor-rich number, my goodness. 8, 12, and 24. Okay, I hope some of the easy ones work. 1 doesn't work, does it? 2, does 2 work? Good. Just straight up 2, vanilla 2, or negative 2? Normal 2. Let's check normal 2. I believe normal 2 works as well, because I did this problem as practice beforehand, but that was yesterday, so I kind of forget. I think you're right. So if I put in 2, I get 16 there, plus 28, minus 20, minus 24. Well, that looks pretty good, doesn't it? Yes, that is indeed 0. So 2, but positive, works. Great. And because this is cubic, isn't that good? Next, we're going to get some linear factor multiplied by a quadratic, so we can just use our quadratic factoring, and we don't have to mess around with dividing any of these by 2 and getting into any really weird or big roots. Super duper. So let's divide it out here. X minus 2, because I remember to flip signs. Dividing into 2t. Why did you write x and not t? Well, it's easy to answer that question because all of the examples have been x's so far. Plus 7t squared, that's fun, sounds like 70. Minus 10t, minus 24. Oh, what? Yeah, don't click over there while you're working. Highly jarring. Okay, so we need to multiply by 2t. We're going to multiply that through 2t cubed. That's 2t squared for those following along at home. Minus 4t cubed. It's squared. Weird. Mouth. Not saying the right things that Pen is writing down. And then we subtract. We get 11t squared minus 10t. So we're going to multiply by plus 11 here. Plus 11t, that is. So multiply that through to get 11t squared minus 22t. Oh, that looks good, doesn't it? Because when I subtract, I get positive 12t minus 24, and those are in the same ratio as this, so I can feel that when I multiply by plus 12, I get to do my happy coefficient dance of that works. 12t minus 24, I get my beautiful 0 happy face remainder. Okay, any remainder, and we divided by the wrong factor, and we have to go back, or we have to find our error. Yeah. Looks good, B? Yeah, good. Okay, so now we could rewrite this right away. We could say 0 is less than t minus 2 multiplied by 2t squared plus 11t plus 12. Now here's something I know about 2t squared plus 11t plus 12, okay? If I were to graph that, it would have a y-intercept up here at 12. It's opening upwards, so if it has roots, and I know it does, they're back there. They're in the negative time. Are we interested in the negative time in this problem? Maybe. I don't know. The problem doesn't specify. But it's weird. Let's acknowledge that it's weird. We might want to know, like, oh, this thing might have had, like, a price that went above or below 24 in the past. We might want to know that. So let's go ahead and find it out. Okay. We'll factor it anyway. Find it out. Because I happen to know those factors. So let's do it. Okay. Let's factor our quadratic in blue. What does this factor into? 2t squared plus 11t plus 12? Huh? 8 and 3 are our magic numbers, so we're gonna break this down into 8t plus 3t. Okay? How did you find those numbers, Connor?
I just went back to the back of this and really started adding them together.
Oh, cool. Yeah, that's really good actually. I wrote down 24. Yeah, that's right. We needed 24. We took out a 2. That's why. But what you do is you take 2 and you multiply it by 12, and that gives you 24. And you want to find the numbers that multiply to 24 and add to 11. Interesting that those are in our factor list. That's great. So now I rewrite my quadratic as, you know, the 11t gets decomposed into those. And then I factor by grouping. 2t times t plus 4 plus 3 multiplied by t plus 4. There's our factorization. So I can rewrite this one as 0 is less than t minus 2 multiplied by t plus 4. So there's that time in the past, negative 4 years ago, or 4 years ago, negative 4 years from now. And then 2t plus 3. Okay? So this is a cubic. It has this end behavior. So it's Q3 to Q1. because it has a positive leading coefficient. So that tells me that when we look at our number line, and this is just, I'm just going to combine my number line thinking and the thinking we've been doing, because people have seen me test so many regions already. I think you're got the idea. So I have minus 3/2 there, and I have minus 4 there. These are our intervals that we're interested in, and we are going to be heading positive in that way and negative in that way, and we must be positive in between those 2 years. So we have this little realm of positivity, and then this happy rosy future where this stock just skyrockets off to huge numbers, off to an infinite value in some infinite future. But this is also a point where we might have to note, like, the domain of this function would have to have some very serious limitations. Does it apply in the past? We don't know. But if it does, then we need to talk about this area in the past where it did have a value above $24 in this range here. And then in the far future, it's going to have a value that's so high that's probably unrealistic. And so the mathematical model probably doesn't map onto reality anymore. So there might be a narrow band of time where this does predict reality. And in business, you would talk about how to manage those types of situations. We're just going to say we'd have to limit our domain. So if we test over here, like f at 10, okay, so that's clearly more than 2. If I put 10 in there, I have 2,000 plus 700 minus 100. That's very much more than 24. So this function here would clearly also be greater than 0, right? So that's true. So beyond 2, it's greater than that. And then in between here, we could test f at minus 2. Looks like an easy one to test. So let's put that in. Okay, if I have p at minus 2, I might as well test in my original function even before I set it equal to 24 and before I kicked it over, because I know what I'm doing, right? So this is going to be 2 times negative 8, so that's negative 16 plus 14, sorry, plus, not 14, plus 28 plus 20, because negative 10 times negative 2, and you can clearly see that that's well more than 24. So our intervals are correct. All right, so I tested the ones that I was looking for. I didn't test all of them, but I can 100% tell you that this is negative over here and this is negative over here based on the function setup, its end behavior, and how these roots are performing. Okay, we don't need to test those. So now we know that, so now we're going to put in our sentence answer, and we're going to say this stock was worth more than $24. Put the $ first. Between 4 years and 18 months ago. So that was negative 3/2 years. Negative is 18 months ago. And will be worth more than $24 2 years from now until infinity years. Don't say things like infinity years, because that's me being real silly, but just after 2 years from now is fine if you're doing a sentence answer. If you're a business person and you say infinity years, people will look at you like you're crazy. I know y'all know that I am crazy, so I say those things. Okay, let's keep going. So we want to know about this rectangular flower bed using 90 feet of fencing. Okay, for what lengths will the area exceed this many feet? Okay, cool. Quadratic. So let's do it. Did I copy this one down on the sheet? Is this on your handout? Yeah? Okay, let's do it. All right, so we are going to set up our rectangular bed. Start with a diagram. It has a length and a width. And we know that 2L plus 2W equals 90. Don't skip this stuff. It's very useful. That tells us L plus W equals 45. and the width could be expressed as 45 minus the length. So then the area of this thing is just equal to length times width, but we have a new way of writing the width, so the area is equal to length multiplied by 45 minus the length. Okay, and so that gives us the area is equal to negative L squared plus 45 L written in standard form. And we want to know when will it exceed 450 feet. Exceed, not exceed or equal, exceed. So we have the area is greater than 450 feet. So this is the area, so that thing is greater than, or 450 is therefore less than that. Okay, so we keep going. And then going to set this equal to 0. 0 is less than negative L squared plus 45L minus 450. Anyone love this when it has the negative leading coefficient? Do you just love that negative leading coefficient? Doesn't it make your life easier? No, it makes your life harder. So get rid of it. So how do we get rid of that negative leading coefficient? Factor it out? Sure, I suppose you could factor it out. Yeah, you could do that, but then I have to keep it. Then I have 0 is less than negative 1 multiplied by L squared minus 45L plus 450.
I'm alright with that.
You're okay? And we flip our alligator. Yeah, is that what you're going to say, B? Yeah, so we could have 0 must therefore be greater than L squared minus 45L plus 450. Is it possible to multiply to 450 and add to 45? I feel like it's not. 45 times 10. No, I don't think so. I don't think that's possible. So let's feed it the quadratic formula. 4 times 10 is, yeah, it does indeed have roots. So let's feed it to the quadratic formula. A is equal to 1, B is equal to minus 45, and C is equal to 450. So we have L is equal to, sorry?
It's possible.
Oh, what is it?
15 and 30.
15 times 30? Oh, good. Yeah, thanks. That saves me a lot of work. Yeah. You had it too? Great. Thanks very much. So 0 is less than L, they're both negative, minus 15, and L minus 30. Very good. And now we have our number line, 15, 30. When is that less than 0? Well, we created a quadratic, so it's even degree polynomial, has now a positive leading coefficient, so we're this end behavior. So I could visualize this thing doing this, and I could tell you that this thing is going to be in between these two values is what we're looking for. That's where it's going to have a negative value, meaning that's where the original pen has a positive value because we flipped signs. So test one of these values. An easy one that's in there might be area at 20. So setting L to 20. Let's work with our original function here and see what we get. A at 20 is equal to negative 20 squared, so that's negative 400. And then 45 times 20 is plus 900, and that equals 500. And in my experience, 500 is indeed bigger than 450. That's why, after we did all our algebra, indeed, when we put in 20 down here, you end up with 5 multiplied by negative 10. And 5 times negative 10 is indeed less than 0. So that's why it's satisfying the conditions that we set up here and satisfying the conditions we set down there. Even though negative 50 is much different than 500, our inequality is telling the truth in all places. So that's why that interval is indeed the interval that we want. So, thank you for the bit of factoring help. It helps me, it saves me going through the quadratic formula to find out the same thing. We have,
First, Nathan just copied me, actually.
sorry?
Nathan copied me, actually.
Should we whisper
Oh.
my ear?
Yeah.
Many of us got it, yeah. So, it's a gardener, right?
Yeah.
And I said meters, but that's of course wrong. And I should say non-inclusive. Just to be a little bit more specific, because we want this to exceed, not exceed or equal. So we need to we can't use 15 feet, we'd have to use 15.1 feet or something ridiculous like that. I don't know why the gardener needs non-exclusive as opposed to inclusive, but hey, their problem. All right, let's keep going. All right, this is the last one. Yeah, all right, let's go. Okay, I see 216 centimeters cubed, so that's 6, right? Okay, so an open top box, cutting a rectangular piece of cardboard. Ah, good to review this one. Why do we want to review this one? It shows up in a lot of places. Hint, hint. So we had this example on the polynomials test, and it was tricky to a lot of people. So let's walk through it. So start with your diagram. 20 centimeters by 14 centimeters. I draw my rectangle of cardboard. Accurate is not super important. This one's 20, this one's 14. We cut out congruent squares from the corner. So I'm going to cut them out from all the sides so that just help me visualize. These are the bits that I cut out. I don't know, how big a piece should I cut out? We don't know. So when we don't know something, we call it X. Okay, so that's X everywhere. You see it? Bing, 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 bing. Making this 20 minus 2x and this 14 minus 2x. Okay, that's now the length of this side here to here and here to here. Okay, that's going to be the dimensions of like the floor plan of your box, the part on the bottom. That's this bit, right? When we fold those sides up. So the diagram for my money is just so useful to help you visualize that and get your algebra set up right. Okay? And then the depth of the box will be x. So we can create an expression for the volume, which is going to be equal to the length times the width times the height. And the volume is therefore equal to 20 minus 2x multiplied by 14 minus 2x multiplied by x itself. Cool. All right. And we want that to be at most. We do not want to exceed a box that would be bigger than 6 by 6 by 6 for some reason. So we're going to set that as the maximum. And it's at most, so yes, we can include that value. I'm going to read it very carefully to set up the proper type of alligator. This is an underscored alligator. Okay, so we have 216 has to be at most. It's greater than or equal to all that stuff. What's that stuff? 2 times 10 minus x. Do you like doing things the hard way or the easy way? 2 times 7 minus x. No one's answered my question. The hard way or the easy way, everyone? Let's do the easy way. Do you want to carry around those extra factors 2 for the whole problem or take them out now? Let's take them out now. Okay, so I'm going to divide both sides of this equation by 4. Am I allowed to do that? Of course. Of course I can divide both sides of the equation by 4. Anyone happen to know 216 divided by 4? Thanks. I'll check it to make sure it's true. But I'm going to divide that by 4 and the other side by 4. I don't know where I wrote down 2. I got 2 2's there. 2 times 2 is 4. That's why I'm dividing by 4. Okay, so these cancel. And then 216, that is indeed 54. Very good. Who said that? Was that Davis? Good job. 54 is less than or equal to 10 minus x times 7 minus x times x, Let's do a little bit of foiling while we're at it so we can save a line. 70 minus 10x minus 7x is minus 17x plus x squared multiplied by x. Okay, so now you guessed it, we're going to subtract 54 from both sides to get 0 is less than or equal to x cubed, writing in standard form because why wouldn't we? This one gives us an x cubed, minus 17x squared, distributing this x in, plus 70x minus 54. And 54 is a factor-rich number. There's a lot of potential factors here, but hey, maybe we should just go ahead and test the easy ones first. Which one works? 1. Ooh, good. 1 works. Okay, add the coefficients together. 1 minus 17, so we're at minus 16, plus 70, so we're at positive 54, minus 54, so we're at 0. Hooray! X's 1 works. Life's not always going to be that easy, but in math class it's often that easy. Okay, so good news. Okay, so let's divide it out. X minus 1, remembering to flip signs, into x cubed minus 17. Anyone able to do these in their heads yet? Not me. Oops, I did it again. It's very jarring. Minus 54. Okay, I hope everyone's having as much fun as me. All right, x squared. We have x cubed minus x squared. We put that in brackets and subtract it. Minus 16x squared. So we're minus a minus. Yeah, be very careful. Minus 16x. So we have minus 16x squared plus 70. He incepted the idea in your mind, and he is not to be trusted. We already knew that. Okay, we're going to put that in brackets and subtract it, which gives us 54x, and of course it does, because we're very lucky that 1 worked. And we multiply by plus 54. Cool. Yeah, and that gives us our happy 0 remainder. Now, does that factor? X squared minus 16x plus 54. To multiply to 54, we can do, 6 times 9, or what else? How do we get that a little bigger?
Sorry?
18 and 3? No, they both need to be negative, right? Yeah, so 18 times 3 does it, but that's kind of going in the wrong direction. So I feel like this is quadratic formula time. Again. But I was wrong once about whether I need a quadratic formula or not. So I'm like, really want to test this.
Wouldn't ask me anything about
54, we are 2 times 3 times 3 times 3. That's the factorization of 54. Grouping at 6 and 9 doesn't work. Grouping at 3 and 18 doesn't quite work. And grouping at 2 and 27 certainly doesn't work. So we are in quadratic formula territory here. Yeah. Does it even... b squared minus 4ac is 16 squared. 16 squared is indeed bigger than 4 times 54. Eva, do you mind grabbing that? Or Emma, do you mind grabbing that?
I'll run to the washer.
Okay, the fun resumes. Last bit. So we need quadratic formula. Let's go. Negative b, so I'm just gonna, sometimes you just write it out, right? Plus or minus 256 minus 4 times 54, which is 216. And that indeed gives us root 40, which is why it didn't factor. So great news, all over 2. So that's equal to, well, root 40 is the same thing as 2 root 10. So, and then we can divide by 2. So this is 8 plus or minus root 10. That's where the roots are. Am I right? Yeah, I am right. Okay, so 8 plus or minus root 10. So let's build our intervals. Okay, so we found one that was really nice, which is 1. Okay, and then so we have 0 plus or minus x minus 1 multiplied by x squared minus 16x plus 54. Set up our intervals. Okay, root 10 is, if we were 8 plus root 10, that's ridiculous because this would be less than 0. So we don't have that. But 8 minus root 10 is ever so slightly bigger than 3. So if we were 8 minus 3, then we are like less than 5. So 14 minus a little bit less than 10 still works. So one of them works. So one of them is reasonable. Okay, but we're still going to consider all of them when we build our interval checker. All of them are bigger than 0, so we have 0 over here, which is not one of them, so I'm not going to write it. 1, 8 minus root 10, and then 8 plus root 10. Okay, so these are our intervals of interest. So we must be, here we have that end behavior. So yeah, it goes off to positive over here, this way, and it's off to negative that way, okay? And then it's going to be in between here, but not there, where we have one that is greater, and then in here it's less than, okay? So we can make a box that's up to 1, and it will be less than 216, but as soon as it hits 1, it's about it's exactly 216. So this realm is okay. If we test f at 0, we'll find that we get 0, and that would certainly be less than 216, so that works. Yeah, because this would be minus 1 here times 54, which is less than 0. So this one is negative, and we want that. So we have this realm of 0 to 1 inclusive is okay. Those are valid dimensions that keep the dimensions of the box below 216 volume. In here, we believe this to be wrong because we have cut roots, so we swapped to positive there. This is the range where we're actually optimizing the size of the box. So in calculus, you'll hunt for the optimal size of the box in there, using the derivative. And then in here, between 8 minus root 10, all the way up to some value, what would be our maximum value of x there that we could admit?
8 plus root 10.
Yeah, 8 plus root 10, but 8 plus root 10 is nonsense because it means we have a box with a negative dimension on one side. What's the maximum value of x that makes sense in this case?
Wait,
2. 14 minus 2x is one of the dimensions of the sides of our box, and that's the one that's giving us like a practical limitation on this situation.
Just less than 7?
Yeah, it has up to 7. Like we could cut 7 out and then have a box that has 0 volume, and that actually satisfies whoever asked this question, which is super weird, but we can tell them that if you really want to, you can make a flat box with 0 volume, and there you go. And yeah, so we have that realm of 8 minus root 10 inclusive all the way to 7 works. So, and it's the union of these two. These are the different area volumes of the box that, dimensions that we can cut out of the squares that produce a volume of the box that does not exceed 216 cubic centimeters. So that's how I would approach that problem. I'll write out my answer. Like cutting 0 out of the sides gives you a flat piece of cardboard. And you say, here's your box. And then someone says, what can I put in it? And you could say, nothing. Then they would say, thanks. And thanks for satisfying my question. But then you cut like 1 centimeter out and you make this like really flat box. Or you cut 8 minus root 10 out and it's really tall and narrow. So visualize these things. And then if you cut 7 out, it's just like a piece of cardboard that folds up like that. And it has no width. So why? It's a weird question, but I like it. There. So practice. Okay. And again, thanks for hanging with me while I do some questions.